Welcome in my channel Digital World. In this video, we will learn how to write VHDL code for FIFO, that is first in first out. So click on ISC Design Suite 14.7. Click on OK. Click on File. Select New Project. This is our folder. Give name FIFO underscore FPGA. This is our folder. Click on Next. Select family Spartan 3E, device XC3S250E, package CP132, speed is 4, synthesis tool is XST, VHDL Verilog, simulator is ISim, VHDL Verilog, preferred language is VHDL. Click on Next, click on Finish. Now this is our device. Right click, New Source, select VHDL model. We should write program, so give file name FIFO underscore 4-bit. This is our file name. This is our path. Click on next. Now define entity for our model. We are using clock. This is sequential circuit. There is one reset signal we are taking. In addition to that, we are taking two more signals. First one is enable write and enable read. So there are two signals we are using, enable read signal, enable write signal, and its direction is in. Then this is FIFO, there we are taking data input, direction is in. We are taking data that is a 4-bit. So in MSB, write it 3 down to 0. In addition to that, we are taking data out. In case of FIFO, direction is out. Select bus and click on 3 down to 0. In case of FIFO, we have to just check memory is full or empty. So we are taking two more signals. First one is full and second one is empty. Both are output. So select out. Both are single bit. So click on next, click on finish. So this is our code. These are comments. We are removing those comments from here. Then just write title. The title is represented with comment. So for comment we are using double dash. So the program is VHDL code for FIFO. First in, first out. Now the second part is we have to zoom this code. Click on zoom in. First part is library declaration. First library is 1164.all. Copy this library and rename this library as unsigned. So second library is unsigned dot all. Then one more arithmetic library we are using. So just modify this 1164 as arith library. Here are also comments. So just remove comments. So the first part is entity declaration. Entity is already defined in the previous block. Clock, reset, enable write, enable read. These are inputs, single bit. Data in direction is in. Number of bits are 4, so 3 down to 0. Data out, output std underscore logic underscore vector 4-bit. Full and empty, both are single bit outputs. Now this is memory part. So we are using memory. So first define memory using type function. You can use any variable to define memory. So we are using memory underscore type, and we are taking array. So we are writing is a array of 0 to 7. 0 to 7 is array of 0 to 7 means there are total 8 locations we are considering. 0 to 7 there are total 8 locations, and at each locations we have to store data. So we can define std underscore logic underscore vector, and at each location we have to store 4 bit of data. So we can write 3 down to 0 and then put semicolon. So this is the way we can define memory with type function. So same memory we can define with signal. So we can write signal like one variable, signal name is memory, and the type of this memory is nothing but memory type. So this keyword we can copy paste as it is. So this is the way that we can define memory with type function. So type memory type is array, that there are total 8 locations from 0 to 7, and at each location we have to store 4 bit of data. So that's why this is 3 down to 0. So this is the first, that how to define memory in our design. Now the second part is we have to write code. So this is our begin, this is architecture begin. Now we have to define, this is sequential statement. So first we have to define process. So define process, which are case sensitive signal. The first one is clock is case sensitive signal, and then we can write begin. So this begin is process begin, and the first begin is architecture begin. Now as we have to go for memory writing, the first we can write the clock. Clock is our sequential statement. So we can define when clock is equal to 1 and clock tick event. Clock tick event means we are checking positive edge. In addition to that, we have to go for memory writing first. So E and W is equal to 1, and what about read signal? So read signal will be 0. Right? Then, so here we are checking 4 conditions. The first one is clock is equal to 1. Second one is and with clock tick event, and write is equal to 1 and read is equal to 0. So if you want to put everything in the bracket, so we can put bracket over here, and then condition. The next one is we have to write data in memory. So we can use signal. We already defined the signal is memory. Here we are using one function, that is of convert integer. So write convert underscore integer. This is our function. In addition to that, as we have to go for memory, we are using two different pointers. So if you want to go for write pointer, if you want to write some data, then we can use write pointer, and this write pointer we are defining to write data in the memory. So the first part is how to assign data. The data we are taking from input, and that is defined in main entity, that will be data in. So we are taking data from input. Those inputs are connected to the switches, and that data we have to store in the this memory. The type of memory is already defined here, and we are using one function, that is of convert integer. We are using pointer in case of write operation, that is called as a write pointer. Now here, as we have to go for 0 to 7, there are total 8 locations are there. So the first thing that we have to increment this write pointer. So write pointer assigned to whatever the previous data we have, that previous data will be incremented by 1. So we are writing write pointer assigned to write pointer plus 1, and the semicolon is mandatory. This is our if statement. So we have to close this with end if. So right here end if. So this is the way that we can store or we can write data in memory. So we can just give some space here, right? So this is our write loop. Now we have to go for read loop. So I will copy paste same as it is to reduce my time. So just copy and paste. What changes I should do? Clock 1, clock tick event is equal to 1. Write pointer is 0 because this is read operation, and read pointer is equal to 1. Now here in right loop, data is already available in the memory. The data I want to transfer to data out. So I will take here output signal that is already defined in the entity. So data out is equal to memory convert integer. So where data we have data in read pointer. So we can write here read ptr, and the rest of the part we will remove from here because this is read operation. And which pointer I want to increment? I want to increment read pointer. So instead of write pointer, we can copy and paste here read pointer. So this is the second loop for read pointer. So this is write operation. Data from data in is transferred to memory, and here read pointer data is available in the memory that will be transferred to data out. So this is another loop. Now the second, I want to check that the memory is empty or full. For that purpose we can use one if statement. If the first one is we have to go for right pointer, so we can check if right pointer is equal to, there are total 8 locations are there, so 0 to 7, but when right pointer is equal to 111, then our memory is full, right? So there is no space for empty. So when 0 to 7, right pointer is 0 to 7, then we can store data into the memory. So we can write here empty is equal to 1, and else condition we can write here else, we can copy the same thing here. In else we can write empty is equal to 0. This is for a right pointer, right? So we can give some space here. Right is equal to 1, then this is else, empty is equal to 0. Now here the loop is end, so we can write here end if condition. So here our loop is end. Now the same thing that we have to copy for read pointer. Okay, so we are reading data from memory for 0 to 7 only. So check the same condition for read pointer. So copy the same loop again. Copy the same loop again. This we are keeping as a read ptr, and this is for write ptr. So write ptr, the we have to just check that memory is full or empty. So here full is equal to 1, and the next one is here we can check full is equal to 0. Next one is end if our process starts previously. So here we can end our process, right? So this is end if and this is end process. Now in our program we use read pointer and write pointer. So we have to go back and we can define those pointers in the signal. So how many bits are there? There are total 4 bits are there, right? So go up where the signals are defined. Signals are always defined between architecture and begin. So define signal. The name of pointer is first pointer we are using write ptr, and the second pointer we are using that is of read ptr. Both are signal, and the type is std underscore logic underscore vector 3 down to 0. So we will copy paste same thing here. Here this is std underscore logic underscore vector 3 down to 0. If I want to initialize first signal as a 000, then we can write here 000 and then write the signal. So this is the way that we can write our code. Now go to the select our file, click on here plus sign in front of synthesis and click on check syntax. Now no error in our design. Then go to the synthesis. After synthesis, click on View RTL Schematic and see the internal architecture. So click on Start with the Explorer wizard. Click on OK. Then click on Add, Create Schematic. So this is schematic. There are multiple inputs are there. Those are defined in our main entity. Just click on this block, then zoom to fit. Okay, so this is our internal architecture that we can observe. Now the next one is we have to simulate this code. So select VHDL file, right click, new source, click here on VHDL Test Bench, give any name, we will give name test underscore FIFO, click on next, click on next, click on finish. Now here we have to write our test bench. So remove those comments. First part is library declaration. Next one is there is empty entity is there, so no change in our code. This is component part. This is signal. Not necessary to change anything here. Directly go to the clock. We are working on positive clock, so you can rename this clock is equal to 1 and clock is equal to 0 here. Just zoom it. Now our job is to write the test cases. So the first test case we can write it here. So first condition we have to just check that enable write is equal to 1. So right here enable w less than equal to 1 and enable read less than equal to 0. This is the first case. Here in the same state we can give data in. So initially I will give the data that is 0001. This is first data I want to store into the memory. Next one is I will wait only for 10 nanoseconds. This clock I want to remove, not needed here. This also we can remove here. Then this wait condition we will remove. Now I will copy this data in 7 times again because we have total 8 locations in our memory. So paste it. I want to change this data. Initially data is 0001. The next data is 0010. I will keep. Next one is third data. This is I will keep here 0100. Next one is 1001. This is fourth data. Next one I will keep here as 0111. Next I will keep here is 3 ones. Next we will keep here all ones. So how many data are stored? 1, 2, 3, 4, 5, 6, 7. The last data I will keep as a all 0. So this is our all 0. So there are total 8 locations are available in our memory, right? So this is the process to write data in the memory. So after this I will make enable write is equal to 0. So I will stop write operation and we will start read operation. So ENR assigned to 1. Now how many cycles we require? We have to store data. We want total delay that is of 80 nanoseconds. So here I will write for wait for At least we require time scale to out your data, that is of 80 nanosecond, and then semicolon. Now this is our file. So you click on simulation. So this is our test code. Then click on ISim Simulator. First check errors. Save this file. No error in our design. So simulate it. So just click here. First zoom full. And we can check here with respect to clock. This is enable write operation. Read is equal to 0. So when write is equal to 1, we are writing data, that is 1, then 2, then here respective data is stored. The last data is 0, and just click over here. In this case we can see read operation. So read is equal to 1, write is equal to 0. This is first data in, that is 0001, that is out first. This is called as FIFO. First in, first out. So first in is 1, first out is 1, first second one is 2, then second out is 2, then 4. So this is 4, then 8, then 3. So here is 1, 2, 4, 8, 3. After that 7 and 15, and the last one is 0. So this is our 0. So after that we can see here empty is equal to 1, right? And here whenever the data is stored in the memory, here full is equal to 1. So there are two flags we have to check. First one is full flag and the second one is empty flag. Now close this. Now click on implementation. Now I want to download this code on board, but on board the clock is very fast, that is of 4 megahertz. So I will divide this clock first. So I will use here signal. One more signal I will take, that is of clock 1. So the first one is clock 1 std underscore logic. Then I will take one more counter here. So with respect to that counter, I will divide my clock first. So define signal CNT, that is of count. That count I will take, that is of big count I will take. So the clock will be divided. So the first one is define std underscore logic underscore vector. Counter I am taking, that is of 24 down to 0. So this will reduce our frequency till 1 hertz. So this is our counter. The first one is we have to define process to divide counter. So right here process, input is clock, and the second input is reset. Then we can write begin here. This is our process begin. Now first define reset. If reset is equal to 1, then whatever the count I am taking, that will be 0. So count assigned to all bits 0. So we can write others 10 equal greater, and then we can put it is 0. All bits are 0. So this is another way we can write the syntax. Next one is we are writing else if condition. If reset is 0, then we can use clock tick event and clock is equal to 1, 10. This is else condition. If this condition is satisfied, then we have to increment our counter, counter assigned to count plus 1. Write it. Now we have to divide the clock, so we can write one counter. If the count CNT is equal to the specific count that we have to divide the frequency, that we can write 110011, then we can write 000101011, then 01, then we can write 7 times 0. This is equivalent code that we have to use 4 megahertz divided by uh, 1 hertz. The equivalent count we can put it over here. And then press. If this condition is satisfied, then we can write clock assigned to 1, else we can write count assigned to 0. So same condition we can copy paste here. If that count is satisfied, then we can make our clock 1. If that count is not there, till that time we are keeping our condition is 0. This is the count model that we can add for our division clock. So this is our begin. This is process begin. If preset is equal to 1, then count is reset. Else if we are incrementing counter from 0 to maximum value. If count is this, then our clock is equal to 1. Else we can write here else condition. For this if we can write else our clock is 0. In this way we can generate divided clock. So this clock is 0 here. Now the process complete. Then we can write end if first, end if, then next end if, and the last one is end process. End process. Now save this and check for syntax. There is one syntax error is there. You click on this, so it shows that there is syntax error. Here single quote is missing. Again save your code, check syntax. Again error is there. Object clock is in mode, right? So here we are taking CLK. So we are defining one signal. This is CLK out. So here we can write CLK1. And this CLK1 is a divided clock that will work input for the second model. So this is my second process. Where the clock is there, we can edit that clock. We can modify that clock by clock 1. So just write here clock 1. This is also clock 1. So this in out mode will be removed. So clock 1 is signal and clock is your input clock. So now there is no error. Click on synthesis. Now select this file FIFO underscore bit. Right click, new source. Select implementation constraint file. Give any name to file. For example, we can give FIFO UCF. Its extension is also UCF, that is user constant file. Click on next, click on finish. I already have UCF, so I will copy paste as it is. Okay, I will just explain you because lack of time. So the first signal is clock. This clock is connected to B8 pin that is given on board. There are total 4 output pins are there. Connect to LEDs G1, P4, N4, N5. Then read and write pin. Those are connected to switches that is of N3 and E2, that is switch number 7 and 6. Empty and full, there are total 2 in output pins are there. Those are also connected to LEDs. So M5, M11, these are two outputs. The data in, we are taking data input from switches, that is a B4, K3, L3, P11, and the reset is connected to push button switch. So that is of A7. I will save this file. So this is user constraint file. Now select bit file, click on implement design. So now the implementation is going on. After implementation, we have to click on generate programming file. So after this, the bit file will be generated, and this is available, that bit file is available in the same folder, f underscore VLSI underscore FIFO FPGA. Now bit file is available in the folder. We are using basis to Digiland board. So Digiland has provided its own adapter. So you can click here on triangle. Now here the device is not connected. So connect device to our PC, and then we can download the code on the FPGA. So this is basis to board. Click on browse. This is FIFO underscore bit file. Click on open. This is warning for clock. Click on S. Then click on program. Same warning. Click S. Now here programming is successful, and the program is stored in our connected FPGA. FPGA board is connected to PC through USB port. There are total 4 data inputs pin. This is write pin, this is read pin. So write is equal to 1 and keep data in the memory. Then we are keeping 0. Now read data is finished. Make write 0 and read 1. And this is the way we are reading data. Initially all bits are 0. Then simply we are making bits 1, and then again we are making bits 0. Here empty and full, these two signals are empty and full. Thank you.